Let's solve some exponential equations. We really like it when we can get the same base on each side, and notice that 64 is a power of 2. So let's write this as 2 to the negative x is equal to 2 to the 6th. That will basically allow us to say, hey, I've got 2 to the something equals 2 to the something. So those two somethings must be equal to each other, and we can set our exponents equal to each other. When we do that, we get negative x is equal to 6, and x then, dividing each side by negative 1, is equal to negative 6. On this next problem, I'm going to write each side as a power of 2 yet again. I can consider that 4 to be a 2 squared raised to the 2x minus 7, and I can think of that 128th to be 2 to the negative 7th. Now on the left-hand side, when I have a power raised again to a power, you know that I'm going to multiply exponents. So that becomes 2 to the 4x minus 14 power is equal now to 2 to the negative 7th. And again, since I have the same base on each side, I can set the exponents equal to each other and just have 4x minus 14 is equal to negative 7. And therefore, adding 14 to both sides, I get 4x is equal to 7, and x is equal to 7/4. Now let's stop for just a second and see what we're doing when we are writing or setting the exponents equal to each other. Technically, what we're doing is we're taking log base 2 of the left and log base 2 of the right. Remember the property that said log base a of a to the x is equal to x, and when you have the same base, that x will pop out? Well, that's what's happening when we take the log base 2 of both sides. That exponent, 4x minus 14 and negative 7, is popping out on each side. So that's essentially what we're doing when we're setting those exponents equal to each other. On problem number 3, I see that both 16 and 8 are powers of 2. So I can write the 16 as 2 to the 4th, again raised to the negative x plus first power, and the 8 can be written as 2 to the 3rd power, again raised to the 5x power. Multiplying exponents, when we have a power to a power, I have 2 to the negative 4x plus 4 is equal to 2 to the 15x. If I take log base 2 of both sides, or essentially set the exponents equal to each other, we have negative 4x plus 4 is equal to 15x, and adding 4x to both sides, we have 4 is equal to 19x, and therefore x will equal 4/19. But what happens when we cannot write the bases with a common base? We have a little bit of a problem here. So what we want to do is we want to take the log of each side. Notice our x is trapped in the exponent position there. We're going to take log of 8 to the x power is equal to log of the 21. What that allows us to do is use the property of exponents that says that x can come out front and rewrite this as x times the log of 8 equals the log of 21. Now, since the log of 8 is a number, we can just divide it off of each side, and we can have x is equal to the log of 21 divided by the log of 8, which we would then use our calculator to approximate, and it turns out that when you round it to about 4 places, you get 1.4641. Now, if you think about this, 8 to the first is 8, and 8 to the second is 64. So we would expect our answer to be between 1 and 2. Note again, if you have a backwards calculator, you're going to have to type this into your calculator as 21, hit the log key, divided by 8, hit the log key, then hit your equal sign in order to get that value. If you have a normal calculator, you don't have to worry about that at all. Let's try another problem where our x's are trapped up in the exponents and we do not have the same base. Again, I'm going to need to take the log of each side. So log of 3 to the x plus first, and by the way, I'm taking the common log. I could be taking the natural log of each side and we'd still get the same answer. Now that I've taken the log of each side, I'm able to bring these exponents out front. So on the left, I'm going to have x plus 1 coming down, make sure it's in parentheses, times the log of 3, equals x times the log of 5. Well, we don't want those parentheses there, so I'm going to distribute kind of to the left, backwards on the left-hand side of this equation, and that will give us x log of 3 plus the log of 3 is equal to x log of 5. Well, we now want to solve for x, but we've got x's on the left and x's on the right, so we need to get all the x's to one side of the equation. So I'm going to leave the log of 3 on the left and subtract this x log 3 over to the other side, giving us x log of 5 minus x log of 3 on the right-hand side. Now, what we're going to want to do is factor on the right-hand side. Since x is multiplied by each of those, we're going to have the log of 5 minus the log of 3 inside of parentheses, and that can be divided off, and you will have x on the right is equal to the log of 3 divided by the log of 5 minus the log of 3. Now, a very common mistake for people to do when they're using their calculator is not to realize that there really should be parentheses around the denominator. You want to divide by the entire difference, not just the first one. So please make sure you type those parentheses in. If your calculator works backwards and you have to kind of have a different sequence, you would be typing in 3, hit your log key, divided by open parentheses, 5, hit your log key, minus 3, hit your log key, close parentheses, and then equals. If you've got a forward calculator, no problems at all. Please check that you can get the same answer here that I have, which should be approximately 2.15066. This time our exponential equation has e to the x in it, so rather than taking the common log, I'm going to take the natural log of each side. So I'm going to have the natural log of 0.3151. I could take the common log, but it's much more convenient to use the natural log this time. When I bring out this power of x, I'm going to have x times the natural log of e is equal to the natural log of 0.3151. Now let's look at this natural log of e. It has a base e there, and we know that anytime we have log base a of a, it's equal to 1. So natural log base e of e is also equal to 1, and basically all we have here is x is equal to the natural log of 0.3151. Now, I like to take the natural log of each side when there's e's involved and common logs otherwise. There are some teachers who prefer that you use natural logs all the time. It's just kind of up to your teacher and how they want to do it. No matter what, you're still going to get to the same answer, and in this case we should get negative 1.15486.